If you travel to the third floor of the Ohio Union, you will find a display of Ohio State inventors in the hallway between the cartoon room and the round meeting room. Here, you will find Richard Olson being referred to as the feline lifesaver. Now, you may be asking yourself, who is Richard Olson? Well, Richard Olson was a professor of veterinary pathobiology here at The Ohio State University from 1969 to 1988. Olson is referred to as the feline lifesaver because he discovered and developed the first effective vaccine for feline leukemia in 1984 during his time here at Ohio State. Not only was this the first effective vaccine for feline leukemia, the most infectious disease in cats according to Cornell University's College of Veterinary Medicine, but Olson's vaccine was also the first vaccine against any cancer in mammals. The feline leukemia virus can be distributed to other cats via saliva, nasal secretions, urine, feces, and milk of infected cats. For example, cat-to-cat transfer of the virus may occur due to a bite wound, mutual grooming, and from infected mother cats to their kittens via their milk. Feline leukemia can cause various blood disorders and may lead to a state of immune deficiency that hinders a cat's ability to protect itself against other infections. The Feline Leukemia Virus Project began at the Comprehensive Cancer Center at The Ohio State University in the mid-1970s, and shortly after welcomed Olson from the Roswell Cancer Institute to the research team. In 1984, after almost 15 years of research, Olson and his colleagues made a discovery that would combat the leading cause of feline mortality. Unlike most vaccines, which destroy or alter the virus so it can't cause disease, Olson's vaccine uses antigens from the virus itself to stimulate the cat's immune system. The vaccine was approved by the U.S. Department of Agriculture in November of 1984 and was then made commercially available. Nowadays, feline leukemia only affects 2 to 3% of all cats in the United States, a dramatic decrease over the past 25 years. The feline leukemia vaccine brought in millions of dollars to the Ohio State University Veterinary School and subsequently allowed for the building of the Ohio State Center of Retrovirus Research in 1989. Today, this center continues to investigate the role of retroviruses in both human and animal cancer. Olson's vaccine also remains as Ohio State's most lucrative patent. As a current pre-vet student here at The Ohio State University, I've prepared numerous feline leukemia vaccines for patients while working as a veterinary assistant at Oakview Veterinary Hospital in Piqua, Ohio. I'm happy to say that I'm now aware of who the feline lifesaver is and just how close to home the revolutionary vaccine in veterinary medicine originates from.
We're into one family of proteins right now that we first discovered in methanogens, and they were the ones that had that stop codon in the middle of the gene.
Yeah.
That turned out to be the pyrrolysine codon.
Right.
And then I started looking a lot at more holistically at all the microbial genomes and realizing that this was a huge family. There are like 10,000 different examples scattered among 2,000 different species.
Oh, wow.
Right? And so, I shouldn't say species, I should say different genomes.
Yeah.
Right? And these usually lack pyrrolysine, That's the surprise. So the pyrrolysine set looks like it came from somewhere, but they're all closely related. The archaeal ones, the bacterial ones, they're pretty closely related together. They look as though they grew out of this tree and somehow acquired this amino acid. The rest of them lack it, right? And because I'm basically a microbial biochemist, I got more and more interested. What are these others doing, and why are they doing it? So, and that's something that turned out to be related to human health.
Oh.
That was an enormous surprise for me. And so but I was very happy because that meant we can get NIH funding for it. So.
Yeah, that's all.
How is it related to human health?
Let's see. You guys have had your organic chemistry. Have you had biochemistry yet?
I've taken one semester.
I've only
Okay.
had organic.
Okay.
But go ahead if it's
trimethylamine, right?
Mm-hmm.
Yeah, nitrogen, 3 methyl groups on it, right? And a proton. And that is found in fish. That's what the primary smell is, right? And actually, one time accidentally dropped a carboy down an elevator shaft,
Oh,
like
no.
15 liters, containing trimethylamine, which completely stinked up a whole building, and we were extremely unpopular for a period of time. Anyway, the trimethylamine is produced in our gut only from microbial activity, and it's done by microbes who are working on compounds that have quaternary amines. So they have basically the trimethylamine group, and then another carbon chain coming off it with various things. Now, as they cleave off the TMA, this generates TMA. Now, TMA gets absorbed into the bloodstream, and once it does, it has to be more or less converted. So there are people, unfortunate people, who have a disease called trimethylaminuria, where they basically lack the enzyme in your liver that turns this into trimethylamine N oxide, which doesn't smell, right? But the folks who have this disease, basically, they lack these enzymes in their liver, and they smell like rotting fish all the time. And I knew one individual had this. It sounds almost comical, but it's tragic, you know. The trimethylamine N oxide, everybody thought was benign for many years. And it turned out that it correlates, and that's the level of it is right now. Some folks up at the Cleveland Clinic found out that it correlated with proclivity toward arteriosclerosis, right? And then further, that if they looked at clinical populations, they could do a really pretty good correlation with how much trimethylamine N oxide was in the serum, and proclivity and the probability of stroke, heart attack, or death within a population of 4,000 folks. And that came about 2011, right? Now, the organisms that do this, right, there have been organisms known to produce trimethylamine for a long time, right? But new enzymes were being discovered which would generate the trimethylamine. Now, I started thinking about this family of proteins where the one we first discovered in the methanogen had trimethylamine in it, right? That was what it used, right? But it uses the pyrrolysine kind of as an adapter molecule to hold the trimethylamine to the right configuration for the enzyme to do its job, take the methyl group off. So I thought, I wonder if the rest of the family uses compounds that already have a handle on them, right? Like an alkyl chain with a carboxyl group on it, or an alcohol, or or a carboxyl in an alcohol. Things that could be, placed very nicely on their own by just other residues, right? And that turned out to be true, right? So I thought the way we proposed it to NIH was that we don't know hardly anything about how these quaternary amines are broken down in the gut. We know they generate trimethylamine, but what if there are other reactions, right?
Yeah.
And we proposed this, and that's what we've been working on lately. We found out that indeed the original hypothesis was correct, that trimethylamine it produced in the gut coming from quaternary amines, right? There's another group of organisms that competes with them for that substrate. Not one group, many groups, right? Using these enzymes. They rip a methyl group off the quaternary amine, making it impossible to turn it into trimethylamine, right? So you get around the generation of the proanthrosclerotic trimethylamine, right? And one of the most exciting things, one of our collaborators is a molecular ecologist, and she's been sequencing really, really deeply the microbiome, and she's been working with me on this project. So she's focused in on the enzymes that make trimethylamine and the enzymes that prevent trimethylamine from being made. And they've been able to show in one population where folks either have arteriosclerosis or they don't, that they can predict based on how many of the TMA fighting and how many of the TMA producing enzymes are present.
Oh, wow.
But
wouldn't that mean that you could then help treat that condition purely by messing with the
possibly,
biome in people's
yes,
guts?
possibly. But that's quite a few steps away, and as you know, scientists try to think one step at a time. But this work is setting the foundation to where either we or other folks will move on to use organisms having this possibly as a nice probiotic, you know, and actually that'd be the next place to logically take it. And I'm debating whether or not I want to go that direction, because my natural inclination is biochemistry, and there's a lot more biochemistry to do. One thing that absolutely astounds me is that when I was getting microbiology courses, folks would say, well, about 25% of our gut is microbes, but they're just there digesting them. And it took this long for people to come to the conclusion that, geez, they really influence a hell of a lot of things, which makes perfect sense. But it just goes to show you how you can be blind with something that's staring you straight in the face.
I guess circling back to kind of what you used to do, I thought we could maybe ask you about what it was like discovering that 22nd amino acid.
We're still working on that. It's just
I still forget about.
Pyrrolysine.
What it was like, yeah.
Mm-hmm.
We call it pyrrolysine.
Oh, pyrrolysine.
Right? Yeah, but one of our collaborators who wasn't in on the discovery, not collaborators, but competitors, likes to call it pyrrolysine. But technically, polypyrrolysine is better, but we like pyrrolysine. I don't know why, but because it's a pyrroline ring, right, that's attached to a lysine, and that's where the name. That's where we came up with the name from, right? But I thought pyrrolysine sounded cool because it kind of sounded like fire, right?
Yeah.
So, anyway, so that was amazing, and most of the things that happen in science begin as really, literally, as you would expect, ideas. And it takes a long time for them to come to fruition. We first thought there was something really unusual going on that might be a new amino acid because we had been sequencing the genes for these enzymes we were discovering. These were, again, methyltransferases, right? And they were all specific for different amines, methylated amines, monomethylamine di-tri. And they were completely different families. There's some relationship between them, but they're really different offshoots off of a tree, really different. And most of this, the stuff that's conserved between them is just things that give them the same general structure. But when we were sequencing through these, we kept running into stop codons, and this was back in the 90s, where they still did science, believe it or not, way back then. And at the time, there were no genomes, right? And so if you were studying a new protein, one of the things you did was to go from the protein sequence back to the gene sequence so you could look at the primary structure of the whole protein, right? And when we did that, we ran smack into stop codons in all three of them, these disparate-looking genes, right? And that was and there's a lot of reasons you could have a stop codon there, and I won't go into all of them, but one of the most exciting was the amino acid. And that took us a while because we ended up in the end collaborating with Michael Chan, right? And he said there might be we want to know what's happening here. There could be a new amino acid there. We had already collaborated with a mass spectrometer spectrometrist who had kind of failed us, right? And but collaborating with Michael and his student Bing Ho. Bing was a great student. She's now a professor out at Connecticut University.